So our objective today is to learn about pyramids and how to figure out lateral area, total area, and volume of those figures. So our objective, is to learn about pyramids. And we're also going to learn about lateral area, total area, which we used to refer to as surface area. I don't know why our book calls it total area now. And then volume. And this comes out of lesson 12-2. So we've got some vocab that we need to deal with, and we're going to have a little bit more complicated time with pyramids than we do with prisms. And that has to do with the fact that we've got, with prisms, we had rectangular sides or square sides, but with pyramids, we've got this base and we come up to a point. So what shape would all the sides be? Triangle. So we come up with a complication of having to figure out the height of the triangle versus the height of the prism or pyramid. So we have two different H's to deal with. So that's why I started using the capital H, even though the book doesn't use it, to represent the height of the shape. So when we're talking about the height of the face, lateral face, that's going to be called something else. Okay? So I'm going to use little h or something else for him. Okay. So let's start with our first word. What on earth is a pyramid? So a pyramid is a three-dimensional figure with a flat base triangular sides and let's say which intersect in a vertex. Okay. When we talked about prisms, there were two basic types. We had the right prisms and we had the oblique prisms, but we only focused in on the right ones because those are the only ones we can really use theorems on. So when we are dealing with pyramids, the only kind of pyramid we can deal with is something that is something we can count on, which would be something that's regular. Okay, so let's give that definition of what is a regular pyramid. So again, regular deals with the notion of same length sides, same angles. But is that for the whole thing? No. It comes in two major components. The base is a regular polygon. So the base is going to have all the sides are congruent, all the angles are congruent. In addition, all lateral edges so those are the edges that go from the base to that vertex point, are congruent. It's going to create those lateral sides are triangles, but if all the lateral edges are congruent, what kind of triangles do they have to be? Isosceles. So all lateral faces are isosceles triangles. Could they be equilateral? It is a possibility, but it's not a requirement. And then I have one more. The altitude, so its measure is the height, meets the base at its center. all of these pieces of information allow you to do a ton of calculations with unknown pieces, so that's pretty good. All right, so I want to go back and refer to a slant height. That is a vocab word, very important that we understand. And the slant height is going to be the height of a lateral face. Okay. So let me draw a quick picture. Okay, I'm not the best drawer. Let me try that. Let me try this piece. Let's do it this way. Let's move them over. That looks better. So this would be considered a square pyramid, because remember, it has to be a regular base. So the only thing that that could be would be a square. So just to label a couple things, this is called a lateral edge. It's where two lateral faces meet. This guy is going to be called a base edge. Sometimes you'll hear that. The height of the triangle, this is your slant height. And the book uses a really weird symbol for the slant height. It's kind of like a cursive L, but they do it in a kind of weird way, so I kind of just use an L. Or sometimes it looks just like this, an italic weird thing. So, and then let's see. Oh, we've got the center. Is here, and if I drop a line down from the vertex to that center, that is the height of the prism, or excuse me, of the pyramid. I didn't label this guy, he is the vertex. Okay. And because the height of the pyramid hits at the center, we can form a little triangle this way, and we can figure out what the length of a side is, knowing that information. If I know the slant height and I know the height of the pyramid, if I know the height of the pyramid and how long a side is, then I can figure out the slant height. So there's a lot of calculations that go on with this. So let's go ahead and let's do, based on a square pyramid, let's do an example. So we have a regular square pyramid. Has base edge 10. And lateral edge is 13. Find its slant height, so that's the A. And B, its height. So I'm going to go back to the drawing I just did, and I'm going to add in the numbers that they just told us. So it says that the base edge is 10 and a lateral edge is 13. Because they gave me the base edge was 10, that tells me this part would be 5. Here's your 13, and now what I need to do is figure out the slant height. I've got a right triangle, so I can use that, and it actually is a Pythagorean triple, if you remember, 5 blank 13, okay, 12. So I'll do that first, calculate it out. So we would do 5 squared plus, I'm going to say slant height squared equals 13 squared. So if you don't recognize it as a Pythagorean triple, you can solve it. Subtract 25, we get L squared equals 144, take the square root, and the slant height is going to be equal to 12. Okay? Part B. So now that I know that that is 12, I'm going to make that a different color. So now I can say he's 12. I know if a base edge is 10, from the center to the base edge would be half of that, or 5. So now what I have is a new triangle where I've got 5 squared plus the height of the pyramid squared is equal to the slant height squared. So I get 25 plus the height squared equals 144. I subtract 25 from both sides, and I get height squared equals 119. I take the square root of both sides, and I get the height is the square root of 119. Okay? Now, what if they asked me just to look at the lateral area of this pyramid? So lateral area now focuses in on the triangle. And how many of them do I have in this particular pyramid? 4. So I'm going to have 4 isosceles triangles that are congruent. So if I figure out the area of 1, multiply by 4, I can get that answer. So let's up here, keeping it on the same page, let's figure out the lateral area. Okay? All right, so all we're going to focus in on now is one face. That is 13 here, 13 here, 10 here, and 12 here. We've calculated that all from the prior examples. So to figure out the area of one triangle, it's 1/2 the base times the height. So that gives me 60. But the lateral area, there's 4 triangles each with an area of 60, and that gives me a lateral area of 240. Okay. So instead of having to do it that way, I actually have a theorem for you that kind of consolidates how to get it, and it kind of goes back to the same one we did for the lateral area of a prism. What was the formula for the lateral area of a prism? You can flip back to your notes and look. What was it? Perimeter times height. Okay. So because we're dealing with triangles, we're going to change the formula slightly. So Theorem 12.3 says the lateral area, which again we refer to as capital L, capital A, of a regular, so this only works for regular pyramids, of a regular pyramid equals half the perimeter of the base times the slant height. So in other words, LA is equal to 1/2 PL. Okay, now remember when we were doing our little magic show? Well, I was doing a little magic show and you were laughing at how silly it was. And we had a rectangle, which remember, that's what the sides are like in prisms. And we drew on a diagonal and cut it apart, and I ended up with 2 congruent triangles. So that relationship is one triangle would be half the area of a rectangle. Okay, so that notion of half shows up here because of that idea. And then I have another one, theorem, this deals with the volume. 12.4 says the volume of a pyramid equals 1/3 the area of the base times the height of the pyramid. Okay, so the hard part here is we've got two sets of formulas and you got to keep them straight. So this one is V equals 1/3 the area of whatever that base is times the height of the pyramid. So capital H is always talking about the height of the whole shape, okay, for both of them. All right, so I'm going to give you one example, and if we have time, we can do another example after that. Okay, everybody good? Yeah. This one says find the volume of the pyramid with the given hexagonal base. Hexagonal. I'm having a hard time drawing today. Okay, now in order for us to study a pyramid, the pyramid has to have a regular base. So when I say hexagonal base, I'm talking about a regular hexagon. So here's what the base looks like. And what we're told, that the base is 6. We're also going to be told the height of the pyramid is 12. Okay, so the problem here is I got to figure out the area of this hexagon. So it's not one of the formulas we know, but it is a regular polygon. So that means the area of this base is going to be 1/2 the apothem times the perimeter. So what we're going to do is take this shape and we're going to figure out the apothem, and then we can do the perimeter is easy. We have 6 sides and measure 6 each. We can get that piece. So let's do some drawing. So the apothem is this blue line. Okay, now hexagons have a very unique relationship when I start drawing triangles. What kind of triangles am I actually getting? 30, 60, 90, because they're equilateral triangles. Okay, and I can get that if I go figure out how many what the measure of all the angles are using the formula quantity n minus 2 times 180. Divide that by 6 because there's 6 angles. I would get 120 for all the angles. And then I'm going to split them in half, drawing these radii. And then that's going to make them 60-degree angles, so I have 30, 60, 90. So I have a hypotenuse of 6. I have a short leg of 3. I have a long leg of 3 radical 3, which happens to be the apothem, excuse me. So I've got that piece. I've got the 1/2 in the formula. The perimeter is going to be 6 sides that measure 6 each. So again, when I'm doing calculations, I can simplify first before calculating and then do the math. So I get the area of the base is going to be 3 times 3 is 9. 9 times 6 is 54 radical 3. Okay. Now I'm going to put that into the volume formula. Volume is 1/3 the area of the base times the height of the pyramid. So I get 1/3 times 54 radical 3 times 12. Now I can take 1/3 of either 54 or 12, and it's best to actually take it of the bigger number. Actually, it doesn't really matter. It's whatever you want to do. I'm going to take it of the bigger number. So that's going to go into 5 once with 2 left over and into 24 8 times. So now I've got 18 radical 3 times 12. So I multiply what 18 and 12 is. I get 36 placeholder 18, 6, 216. So the volume of this particular shape is 216 radical 3. Now they didn't give me any labels, so that's as far as my answer can go. Okay? And I am going to forewarn you, because we're dealing with triangles, what may end up happening when you have a triangular base is that the center point ends up being, you end up needing to use that Theorem 10.4 that deals with the medians of a triangle that intersect a point that's 2/3 of the distance from each vertex to the midpoint of the opposite side. So just to forewarn you that Theorem 10.4 shows up again in this unit, especially with our pyramids. Okay? That's it for the notes.